A harmonic series is also known as a p-series, which is a more general term, but the p-value is equal to 1. So the general formula for a p-series is as follows. So p-series always converge when the p-value is greater than 1. When I say converge, I mean that it approaches a finite value. So I'll leave a link to an article that shows why this is true, but it has to do with the integral test. So let's move on from that. So what we're going to do is define something called a zeta function, and essentially the zeta function just gives a p-series given a p-value. But I hear you say, how does this have anything to do with prime numbers? That's why we talk about the Euler product formula. But instead of just giving you the formula and talking about it, I want to discover it together. So let's just start off with the zeta function and its expansion. So we have this long formula. And then what I'm going to do is I'm going to multiply both sides of the equation by the second term in the sequence. So in this case, it's just 1 by 2 to the power of s. So you can see on the right side, we have every single multiple of 2 in the denominator. So if we want to remove that from the original zeta function, we just do zeta of s minus 1/2 to the power of s times zeta of s. So that's what we're going to do. And we have the remaining terms. Then we're going to repeat the same process, except for the second term of this new sequence. So we're going to multiply both sides by the second term of the sequence now, which is 1 by 3 to the power of s. So if we do that, we have these terms, and then we subtract them from the original series. And then we do this again, and then again, and then again. So if you notice that every time we do this, we're subtracting multiples of each number. So the second term in our sequence is always going to be prime. So if we continue this process to infinity, we get something like this. And if we move all the primes to the other side, writing this formally, we have sigma 1 over n to the s is equal to 1 over 1 minus p to the negative s for every single prime number. This is called the Euler product formula. It gives us the first relation between the zeta function and prime numbers. And since this formula was discovered in 1737, modern study of prime numbers has always been based on the zeta function. The idea for the prime quantum function is pretty simple. Let's give it a number x, tell me the number of primes below that number. And this might be confusing, but we actually denote this function by the character pi. So a few examples are pi of 5 is 3, pi of 10 is 4, pi of 20 is 8. So the prime counting function is a step function, means it's not continuous. So let's look at the graph of the prime counting function. And this function was introduced by Gauss in the 18th century. And another thing Gauss showed was that you could approximate the value of the prime counting function with the expression x divided by ln of x. This fact is called the prime number theorem. More formally written, it states that the limit as x approaches infinity of pi of x divided by x by ln x is equal to 1. So if we take a look at this graph, that's pi of x by x by ln of x, you can see how it closely approaches 1 as x approaches infinity. So another result we can take from the prime number theorem is that the probability that a random chosen number is prime is roughly 1 by ln of x. In terms of the prime counting function, the prime number theorem tells us that each average step in the prime counting function is around ln of x. However, there's actually a better function to approximate the prime counting function. What's the indefinite integral of 1 over ln of x? So my first instinct would just be to, let's just plug it in Wolfram alpha. So I did that and we get Li of x plus c. This Li function is called the logarithmic integral function. The indefinite integral of 1 over ln of t cannot actually be described algebraically, so we use this special function to describe it. It actually turns out that Li of x is a better approximation for the prime counting function than x by ln of x. Here, let's look at all three of them graphed. Wikipedia has a nice table that shows numerically why this is true. You can pause and take a look at this table, but for now I'm just gonna skip it. Now let's go back to the prime number theorem. Since Li of x approximates pi of x, the limit as x approaches infinity of pi of x divided by Li of x is 1. This way of approximating the prime counting function by the logarithmic integral function was discovered by Dirichlet after Gauss made the prime number German mathematician who studied fields like analysis, number theory, and differential geometry. I'm sure you've heard his name before in your calculus class. For example, he came up with Riemann sums. So he was one of the first to study what happens when you extend the domain of the zeta function from real numbers to complex numbers. So 3blue11 has made a fantastic video on the Riemann zeta function, and you should probably watch it, but let's quickly go over what the Riemann zeta function is. So the Riemann zeta function is essentially the zeta function that we talked about earlier, except we extend the domain to the whole complex domain, and it converges for a real component greater than 1. Let's look at why this is true. So let's look at some input a plus bi into the Riemann zeta function. So let's just focus on the first term, which is 1/2 to the s. So it's just 1/2 to the a plus bi, which we can split into 1/2 to the a times 1/2 to the bi. But what does it mean to take a complex exponent? And what this turns out is that a complex exponent just accounts for some rotation along the unit circle with no change in the magnitude. I've left a link to a video by 3blue11 again that explains this pretty well, but what this means for us is that the magnitude of each term in the Riemann zeta function only depends on the real component. And so Riemann zeta function converges for RE of z, which is greater than 1. But what about the other side of the Riemann zeta function, where the real component is less than or equal to 1? So Riemann used something called analytic continuation. Basically, he just extended the domain of the zeta function by quote-unquote flipping it across that. So what Riemann studied was the zeros of the zeta function. So to examine this, let's look at the formula of this Riemann zeta function with analytic continuation. So this term right here is the gamma function. See, the idea of the gamma function is to provide a continuous function that goes through factorial points. Since I'm very lazy, I'm just going to pull a clip from an old video of me talking about the gamma function. The gamma function, which looks like this, is equal to n minus 1 factorial for all positive n. The gamma function is an extremely important function that appears all over math. It gives us a way to extend the familiar domain of factorials from positive integers to positive real and even complex numbers. Basically, the goal of the gamma function was to define a smooth curve that would go through factorial points. Here, I've plotted 3 points, which all satisfy f of x is equal to n minus 1 factorial. So for x minus 1, the y coordinate is 1 minus 1 factorial, which is 1. Similarly, for x is equal to 2, the y coordinate is 2 minus 1 factorial, which is equal to 1. And finally, for x is equal to 3, the y coordinate is 3 minus 1 factorial, which is equal to 2. The gamma function is defined as follows. It's the integral from 0 to infinity of e to the negative t times t to the power of z minus 1. Here's a challenge for you. Try to see why this equals n minus 1 for positive integers. Hint, it has to do with integration by parts.
No, gracias.
Thank you, me from 6 months ago. By the way, if you haven't checked out that video, I highly recommend you. So, going back to the Riemann zeta function, let's take a look at the formula and see when it equals 0. So this sine term should equal 0 for all negative integers. These zeros are called trivial zeros. For positive even integers, the gamma function forms something called a pole, which cancels out the 0 of the sine function. I'm not going to explain what this means here, but I've left a few links in the description. So a nice illustration of the trivial zeros of the Riemann zeta function would be to graph the real components of both the input and the output. Look how zeta equals 0 at negative real numbers. So going back to the Euler product formula, if the real component of the function is greater than 1, one of the products have to be equal to 0 for zeta to be equal to 0. And this is impossible because of Euclid's theorem, which, if you remember, states that there are an infinite number of primes. So the right component cannot be equal to 0. So that means that the non-trivial zeros of the Riemann zeta function have to have real component between 0 and 1. So let's see if we can visualize. Probably that complex functions are like pretty hard to visualize, but I'm gonna try my best. So what we're gonna do is we're gonna fix the real component of our input, and we'll have the x-axis be the imaginary. Then we're gonna have two graphs, one for the real component and 1 for the imaginary component of our output. So since we know that all the zeros we're looking for are between 0 and 1, let's vary the real component from 0 to 1. I'm going to play the animation out.
Really?
So now let's take a look at these red circles and focus on the red circles and play the animation once more. So before we start, let's look at the imaginary component. Notice how it equals 0 at this point. Now let's play the animation. Let's play it once more. Stop. Notice that RE of S is equal to 0.5. The real component intersects with the imaginary component at 0. Let's move a little bit more front to RE of S is equal to 0.6. And notice how there are no zeros in the zeta function. So this is the famous Riemann hypothesis, what states that all the non-trivial zeros of the Riemann zeta function have real component 1.5 or 0.5. The Clay Math Institute has offered $1 million to anyone who can prove this fact.
Uy, ¿cómo que?
So I'm sure you're wondering how all of this has any connection to the prime numbers. So for this topic, let's go back to the prime number theorem. Remember how we could approximate the value of the prime counting function pi of x using the logarithmic integral function? Well, the Riemann hypothesis helps us talk about the error by which the logarithmic integral function can approximate this function. If the Riemann hypothesis is true, this error is no more than some function of order square root of x times ln of x. And this goes both ways. If you can prove that the error is a function of order square root of x times log of x, the Riemann hypothesis is true. A more direct question is, how is the Riemann hypothesis and primes related? So this would be where I talk about Riemann's explicit formula. Riemann's explicit formula gives us a direct formula for the prime counting function. And the second term over here is a sum of all non-trivial zeros p of the Riemann zeta function. Let's look at an animation of this function.
¿Cuántos ojos
Let me
tiene?
graph the prime counting function, and then let me graph the Riemann explicit
Segundo,
formula
tengo que
using
concentrar.
one trivial zero of the zeta function. Now let's increase the trivial zeros and let's see how the graph becomes a better and better product.
Pausa. 12, 10. Es posible. ¿Cuántos ojos tenía? Tenía 10, gasté 8. 4. Dios mío.